We are going to go through a quick review of how this Astro 93 was developed. There are some questions came up, and just give you a flavor of where these came about. So, how were the empirical equations developed from the Astro road test? How was the PSI developed, and how were the original equations modified, and why? So, Astro road test, they calculated the pavement distresses for known loading. They developed generalized metrics for overall pavement distress. They correlated that to loading parameters and pavement design. So basically, they took the Astro road test loading numbers and then converted them to develop pavement design in nomographs. They related layer thickness to performance, and then finally developed more subgrade modulus reliability and damage equations, and led to the nomograph. So this is what it looks like, right? This is the same Astro loop test that was done, and overview of the road itself. There were 6 loops, 2 lanes each. Test pavement sections on straight segments because they wanted to remove the impact of lateral stresses or shear. The trucks on loop 1 there was no loading because they only looked at environmental effects. That's how they got the delta PSI frost heave and swelling. They looked at no loading on loop 1. Total of 284 flexible sections, 44 were duplicates, 264 were rigid sections. Flexible sections, bituminous AC surfacing over crushed dolomite, limestone over natural subgrade, and the distresses observed was rut depth. Slope variance is the IRI that I explained to you with the 2 points and the change. That's the old version of IRI. Cracking and patching. These were the things that were measured in Illinois. Original pavement conditions rating, pavement serviceability, that's the PSR. That's the rating that I told you earlier, that you do a subjective rating, and everybody did that subjectively from very poor to very good, right? 5. And they were subjective and costly. So there was a need to develop a new system of rating, the PSI, right? That's how the PSI came about. Generalized equation was developed to predict PSR based on these measured distresses, and that became the PSI, right? The PSI accounted for actual distresses. Pavement with one significant variable distress with others considered within the continuity. So basically, if one of the sections of flexible cracking dictated, that kind of dominated the PSI equation. So right here, this is the first equation, right? PSI of 5.03, 5 being a perfect condition, times 1 log 10, 1 plus SV, that's the roughness. Rut depth, K is surface cracking, and P is patching. So you can see going from 5 to almost 0. That was one of the first developments of PSI equation that was related to PSI. Slope variance was the same as before, as IRI wasn't developed until 1980s. This was better than the PSR, which is subjective, right? And theoretically, a perfect road would have a PSI of 5.03 in this case. But even new roads will not have a perfect, right? As you can see from the factors right here, 0.03, that means it's almost 3%. Absolutely minimal impact of surface cracking and patching is what you're seeing here, and a significant impact of rut depth right here, right? And then 1.91 is the roughness. You can see from this equation that if you have cracking or patching, it did not have too much impact at that time in the PSI. So right here, you are looking at the Astro equation, right? Pavement serviceability rating going from 0. This is going from 0 to 10, and you had this equation. Terminal serviceability level. When it was 3, 12% of people said it was unacceptable. And when it was 2, 85% said it was unacceptable. That's how they came up with that bottom line number. What will I call the baseline, right? So remember that we are going from 5 to 2.5, 4 to 2.0. So where did that number come from? This is where it came from, where 85% said it's unacceptable, and that became the criteria. So PSR panel was asked to rate whether the payment was acceptable, yes or no, and 50% acceptable point was between 2.5. Right. So this is how they came up. So the reason I like these slides is because it gets to how they came up with this number. They're not magical, just came up. There was some thought process to it, and hopefully it gives you some appreciation as to where it came from. Well, the first days, I think the index days are explained later. So this is the flexible payment. You started from 4.5, and you have 18 gives single axles, 48 gives, I think this is tandem axles, and I'm going to get to this 5, 6, 12. I don't remember offhand, but it's in the next slide. And then you have rigid payments. You see the drop in the yes. Right here. They are here it is explained. Once PSI was developed, average new PSI for flexible was 4.2, right? 4.5 for rigid. Considered fail at 1.5, right? That's what they found in the test. So, flexible payments application weight related to deflections in test payments. Rigid looked at they found that environmental effects may have less impact. Let's go back. Upper x-axis, time. Index days were 2 weeks apart. So they were measured 2 weeks apart. Let's go back up. That's the upper axis. So right here, they were approximately 11 days apart, right? So that's what we are looking at. That's when the data was measured. That's the, so let's go back. Time is index days were 2 weeks apart, note uneven spacing. Upper two numbers, loads in kips, load factor, 1 for single, 2 for tandem. And let's go back, 1 for single, 2 for tandem, right? A flexible layer thickness, lower three numbers. Flexible layer thickness, top, middle, bottom. So 5 inch, 3 inch, 4 inch. Now I don't know, right? So those are the three, those are the payment sections, 5, 6, and 12, 5, 6, and 12. That's what the flexible layer. Let's go back. Rigid layer, slab, 0 to 15 inches non-reinforced, 1 to 40 feet reinforced. And let's go back. So again, 18, 1, 0, 8, and 3. And right here, 0 for 15, 1 for 40. Okay, so okay, so right here, 0 for 15 feet slab, 1 for 40. That's what that means. So each one has a meaning here, 0 for 15 feet, 1 for 40 feet. So there's a key index is related to this. Okay. Load counts and measurements are recorded every 11 index days, or whenever PSI interval reach an interval of 0.5. Now I can't be found, right? So whenever there's a drop of 0.5, they were recorded every 11 days, or whenever PSI reach an interval of 0.5. So let me go back up. So you're looking at drop in 0.5 of PSI. That's when they noted the data, or every 11 index days. Next one. Flexible, when sections were relatively stiff, the payment deteriorated slowly and vice versa. So the very stiff section performed very well. A rigid payment should accelerate deterioration. For flexible surface is weaker early on and loss due to environmental conditions. So again, delta PSI long term is. All right, let's look at the generalized curve. P is the serviceability index. Okay. Right here, that is the curve, 4.2 minus 2.7, this is section 305. Beta is, this is the fit they provided, and rho here is 132,000 passes. So right here, they have fit that from 4.2 to 2.7, that's this equation right there. Okay. Right here, you have another fit going in this direction, 4.5 minus 3.0, and you can see the raw data here. You have 3 data points here, and look at the data points here. So it's not a clear-cut shape, but they fit it between the two. Okay, between the two sections. Right here, this fell pretty decent. So first steps were here. P is equal to P naught delta P. W is the number of easels, and that's the drop. Environmental and traffic effective PSI are not separated. Same axis as the last slide. Intercept is the starting PSI. What does it mean? The y-intercept is the starting PSI. That's what it means. I'm going to go back and explain each one of those. Starting intercept is 4.2 and 4.5. That's what this is. Okay. So set to hit terminal PSI when W loading counts equals to rho. So basically, what it is doing is it forces you to determine. You are saying that it drops at 1.5. It's 1.5 is the terminal. It is forcing 1.5 to be one of the points. That's your final point right here because they consider that as a failure. So it starts from 4.5 to 1.5 for rigid. It starts from 4.2 to 1.5 for flexible. It's forcing those 2 points and it is fitting between the 2 points. That's what it's saying. So right here, set to hit terminal PSI when W counts equal to rho. So you calculate what the rho is, right? So you can predict what the rho is going to be when it hits 1.5. So at 832,000 passes, it reaches the terminal PSI of 1.5. For flexible, it reaches 942,000 passes at delta PSI, a PSI of 1.5. Okay. Beta is a power which describes the shape. Less than 1 is concave up, 1 is linear, and greater than 1 is concave down. And that's what you see right here. So it's concave down and automatically give you your beta. Things to note. Curves become less accurate at very low PSI. Critical point around 2.5 to 3.0 happens to coincide with the 50% acceptable rate. So actual road test assumed that 1.5 as failure, but they found that at 2.5, 3.0 is a better failure criteria than 1.5. Past which the pavement seems to fail rapidly. If you go back here, this is what you are seeing. You can see at 2.5, it just after 3.5, it's just dropping drastically. Right? So they are saying that putting 1.5 was not the best way. You have to cap it a little early. The bottom line has to say 2.5, and they are saying that it coincided well with the driver, which they said it was unacceptable. 52% said it was unacceptable. Know that these cases, the curve overestimates the number of condition cycles to failure. Next one, determining beta and rho. Step number 1. How do you determine the functions? That's the equation. Log is the pixels. Log of the rho minus the drop in the P0 to P at any point. So right here, the y-axis is starting from 4.2 to minus P. So as the traffic goes up, since it's a subtraction, the PSI is dropping. It's a subtraction, 4.2 minus, so it's dropping. And you can see that's your equation right here. Beta is calculated with this equation, 0.4 minus so on. So that's your first beta for section 306. And that's your another data set of D for rigid pavements is right here. And I'm going to explain what these numbers are, L1, L2, and so on and so forth. And then rho is right there. Right, let's look at this. The coefficients beta and rho needed to be calculated using pavement design and loading conditions. Both of the equations, the loop of the slides are from taking log of both sides. You have the log of 4.2 and log of W. The right one is important in this slide. Determining directly through linearization. So when you do log scale, it turns out to be a linear curve. The two graphs show the result of using log of loading and the log of P for dependent variables. So log of P0 minus P and log of W. Beta is the slope of the line. Beta is the slope of this line, and and the intercept is log of delta P minus beta intercept when W is 1. So when you have log of W is 1, that means W is 1 right here. Right? Log of W is 0. So that's your intercept right here. Okay, beta can be found via linear regression and rho can be found by setting P equal to terminal PSI. So that's simple. Let's look at this. Now, let me go back. So before we get into this equation, I want to know what this means. Models are less when selecting forms for these empirical equations. Models with smaller log residues were preferred. Models with less complex algebraic form were preferred. P is the thickness index. Okay. If D2 is for rigid pavements, right? And thickness index was something before SN was developed. SN came afterwards. So D was almost like SN, but it was not actually the thickness. So then you are looking at because from that type of something. L1 is the load applied to the section and lane in question. Okay, so let's go back up here. L1 is the load. Where is L1? L1 is the load applied to the section and the lane in question. L2 is the loading factor, 1 for single axle and 2 for tandem. So that's what those numbers are. Okay. All others were constant and were solved. And these are explaining a little bit of that. So right here, when you solve that, you get this final equation, and this D was the thickness index, and that turned out to be the structural number of the structural number. Right here, by taking log of the previous equation for rho, we get the equation above. The resulting equation at the bottom, that's your final equation for the nomograph. So again, D is the SN required as per solve. Determine required thickness index. This is how they determine the thickness index. This is the loading applications from left to right, and this is your SN number. Remember, thickness index is not the thickness, it's the SN number, and you can see your as you are increasing the terminal P is 2.2 for single axle load, and you are seeing the you are seeing for 30 kips loading, 18 kips and 6 kips, you're looking your SN required and number of axles you can take. For example, SN of 4 or 5, you are looking at almost 1200 repetitions, right? SN of 1, it's almost much lower. You can see the drop in the delta place. Sorry, 6,000 pound. It's just 6,000 pound load of 1,000 repetitions. This is for 1.5 kilo. And then 30,000 pound load, 1,000 repetitions of SN of 100. Okay, so that's what this is there. And then questions. Thickness index can be back calculated from overall curve equation. Bandwidths are requiring twice the average horizontal deviation. These confidence bands encompass about 90% of the data. Test section did not reach failure by the end of the test fall within the extrapolated sections. Some of these sections did not fail and they were extrapolated. Keep in mind that these are not expressed in ESLs. Thickness index is not the same as structural number, but it eventually became one the next stages. Now your clear thickness to structural number. Thickness index B is the precursor to the structural number. Layer coefficients A were applied to the thickness of each layer in the flexible system to translate the thickness into layers contribution to resistance. Right, so that's SN is equal to A times D. Right, and then A was calculated based on resilient modulus, E value, CBR, or Marshall stability. Right, so that's the equation for A log, the equation that I gave you for A values. That is dependent on the resilient modulus, CBR value, and the Marshall stability. Initial layer coefficients in the Ashton road test were found empirically for each loop. So right here, HMA layer coefficients from Ashton in 1962. So you're looking at different loops, structural coefficients, and you have test section, you've got the fit, and then you have for different layers. Most likely, known thickness index were found from main equations. For surface course, they use the section with the same base and same subbase thickness. So they kept the foundation the same, but with variable surface layer thicknesses, and they determine the thickness index. Modern methods. Layer coefficients have been commonly correlated to resilient modulus, and this is the equation I showed to you earlier. This is from the Ashton 93, and then you have the structural coefficient 0.4 for 40,000, 400,000, and then there were other charts developed at different times. Empirical equations were developed for later studies. Here are some of the equations I showed you earlier, 0.249 and 0.27 log V3. And then we had some other equations for drainage coefficient as well. Was developed by scaling down the strength of the base and subbase, as I told you earlier. If you do not have the ability to drain the material, to remove the material water out, you would reduce the strength of the material depending on the person passing 200. I forgot the oh yeah, average annual rainfall. So that's how they came up with each of the drainage coefficients. And finally, structural number. Thickness index was replaced with structural number, and that's what we got the equation. This is how they developed with E was replaced with Sn, and that's how they came up with these equations. Adjustments for the subgrade modulus. After road test was they determined the resident modulus of 3000 psi. Later studies with different suburbs were determined for different performance data. And this is what you see, the change in the, so the AASHTO was done for 3000, and now if it lasted 10,000, there was an increase in log of 10, that is almost 10 times, right? And if the modulus became almost 500, there was almost 100, log of 2, minus 2, so almost 100, so at 3000 it was 1. And an adjustment was needed to be made to the original equation, so that's what we are looking at, is that all the adjustments were made to 3000 psi, and then I can explain to you about the damage. So for all versions of the equation, I've used the mean of each variable reliability of 50%. One final adjustment was made to account for thickness, material properties, and traffic flow. This is the variability I explained. S0 of 0.45, 0.33, 3.35. So accounting for variability in the thicknesses, material properties, and traffic flow. S0 was around 0.45 to 0.949 for flexible pavements. And this is how the nomograph was developed. This equation was translated to something like this. So this is just a recap of how you calculate the structure sign. So we work from top to bottom, right? Yeah. So I think this nomographs about are these turning lines. These turning lines is a graphical way of solving the same equation. That's all. So, pardon? Yeah. Find the SN number. Yeah, find the SN number. So I can ignore this entire thing, plug this equation, you'll get the same answer. That's all. So the turning line is a very, earlier version where calculators were very expensive at that time, right? So they do a simple nomograph check, and then they can come from here, they turn this, and it'll come out to this. So if many times I tell my student to just go into Excel, plug this in, ignore this entire nomograph, and plug this in. This is the ESELS, this is the standard deviation. CR can be found from the table. SN required to protect the subgrade. We know the MR, we can layer your protect. Any other questions? Any questions online? I just give you a little snapshot of how these were developed. And then right here, I think I covered some of this before. You start from top to bottom, right? And then you have D1, SN over A1, then D2, SN2, SN3, and these are all required, right? Let's go through this again. So design a 3-layer system. You have ESELs of 18 or 19 million psi, right? Reliability of 95%, right? And S0 of 0.35. Okay, so very tight reliability. Delta PSI of 2.1. Okay. So from the nomograph, you start from the top. SN required to protect the subgrade, the base 30,000 is SN2, 3.2. Right. SN required to protect the sub base 11,000 psi. 4.5. SN required to protect 5700 psi is 5.6. Right. Again, I don't like the numbers 1, 2, and 3 because I would rather just clearly state SN required to protect. So it is very clear that 3.2 to protect 30,000, 4.5 to 11,000, 5.7. Top to bottom I work. So let's start from the top. 3.2 is required to protect this, and you need 7.6 inches. Right? And you round it to 8 inches. We did this math. Then you go to the next layer. Right? The total summation of SN required is 4.5 right there. Right? And it is provided by 0.42 times 8. I provided 8 inches, and 0.14 is given to you, 1.2 is given. Okay. And you get 6.8 inches. I convert round to half. Then I go to the bottom. A 5.6 is required to protect the 5700, and I do the math. Minus 0.42 times 8 minus 0.147 times 7, and I'll get 11.1 inches. I can do 11.5. I did 12, but I can do 11.5 inches. That will be your final answer for these conditions. Questions? Something I would do in the tutorial as well. Brush tone is there. You guys have access to the textbook? Yeah, go ahead. Go ahead.
So, like we calculate SN for the subbase, base, and the layer. So, we calculate, we need to calculate SN for the bearing force, like in the upper where we haven't calculated for the 44. It is 400,000 psi.
Yeah, 400 is on the surface. It has not been protected. So you're not protecting the 400,000. There's nothing above. Right? Does that make sense to you? So you're protecting the layer below. So the above is the lower. Right? So that has to protect the layer below. The one protects the layer. Does that answer it? You should try this out. Right? This is the reason I like this problem is because it kind of really brings in the entire traffic calculation, design results, the entire Astro 93 design. This is what we have done before. But, let's look at this. AI and Astro comparison, right? Reliability, asphalt instrument does not consider. Astro method does consider. Directly, AI method indirectly considers reliability through the percentile value. Covered that last yesterday, but indirectly. Environmental factors due to freeze thaw and frost heave, that is the delta PSI from stop heave, does allow, does not allow, affected by changing. Long-term environment does not account for and does account for. And right, and then the subgrid modulus is the percentile value, that's the one I mentioned, and this depends on the damage, the huge factor. AI method uses fatigue and rutting relationship to determine repetitions to failure. There are no empirical statistical relationship required to different. True or false? Can anybody answer that? Now that we went through the whole development of NF, there are no empirical statistical relationship required to different. Yes. There is no, or there is no. False, true, will explain. True, false.
Also, but no, it is false because the performance criteria is based on the field performance. On the basis of the field, like it is driven by the travelers and the like what we are feeling. It is basically that.
Correct. So yes, there is empirical. It's not purely mechanistic. It is a mechanistic empirical design. You cannot escape statistical relationship. That is it. So NF of field, right? Remember, I shifted the curve up or down from NF of field, lab to field. That is the statistical piece. You see what I'm saying? That is the statistical piece. I made the leap of faith because there is no way I could have got tracking. So NF of field is completely independent, depend on the failure criteria. So yes, the answer is false. It is required. You have to make an empirical jump by shifting the curve, and that is why empirical relationship is required. If you escape this, I want you to clearly understand. If you do not need any empirical or statistical relationship, that means I can magically predict cracking and rutting in my model. Not possible, right? What the layperson sees, I cannot predict that, not possible, too much uncertainty. All right, next is, any question before I move to conclusion? All right. We'll go into concrete, rigid payments, lot of concepts here on concrete.
Sir,
Yeah,
sir,
yes.
sir, in India we do the effective CTR. Bottom embankment subgrade is CTR, the sphere is different, and subgrade CTR is different. Okay, the effective CTR.
Okay.
So in this method, is there any possibility to find out this effective CTR?
So there are relationships to correlate CBR to modulus. So there is a straight equation. One of the equations is, I think, MR is 1500 times CBR. So yeah, somehow you have to correlate CBR to modulus values. So if I go back to chapter 6, I think there is a correlation between CBR and MR values, correct?
And CBR for less than 5%, CBR
It is there.
Yeah,
It is there.
it is there, right?
also even in IIM.
Yeah, exactly. So there are equations there, right? So I'm trying to find the equation here as well. Yeah.
But how to find out this?
How to?
How to find out
How to find out this equivalent CPR? You can call it as a effective CPR or effective modulus of Brazilian.
Given for CPR value, not for the effective CPR. Equation is given, it is only for the CPR. It is not given for the effective CPR.
What is this effective CBR? Really a different thing.
Actually, we put in another subgrade layer of another soil, then calculate the
Yeah.
plus subgrade and that. Effective CPR is like putting
combination of CBR of
Oh yeah. So composite CBR. Composite CBR.
natural soil and
There's no way. Okay. All right. Again. So you are looking at effective CBR. The only way you will get an effective CBR of a composite layer is if you do a non-destructive test. NDT. So if you want, I can do a quick evaluation of NDT before I go into rigid pavement design, and that would be a very valuable thing to go through. You know how to do non-destructive testing? Falling with deflectometer. You know how to calculate? Do you want me to do that? Quick recap. How does HWT works? Do you guys know? Okay, let me cover that. That's also very important. Then I'll go to pavement design.
Okay.
All right, I'm going to go through. I'm going to cover the concept of. If it's okay, I'm going to cover the concept of how you could get. The question here is, how do I get modulus of a composite? So, right. Let me just explain this. So when we do falling wave deflectometer. Can they see this?
Yes, sir.
Okay. Okay. So I'm going to explain this in detail. Very fascinating. Let's look at this. if I want to get the subgrade, if I have a 4-layer system, right? E1, E2, E3, and E4. And now I do a falling weight deflectometer. What is a falling weight deflectometer? Is that I apply a load, go ahead, complete it, and apply dynamic load, you kick it, and what do you measure? You measure 7 deflections, right? Right. So you have 7 sensors, right? 1, 6, and the 7th one is somewhere. Okay. Everybody with me? So the entire system acts like a composite beam. Okay, so consider for a second, structural engineering concept, that this entire thing is a composite beam lying on this natural surface. Everybody with me so far? Okay. Now, what is my goal? My goal is to get E1, E2, E3, E4 without making any codes, without doing any testing. I want to determine what those modulus values are. Okay. So I hit the pavement, and now it's going to, if I hit the pavement, it's going to deform. I don't want to make this too busy. It's going to deform like this. Right. The highest under the low, lowest away from the low. All right, the 7 deflections. Can everybody see that? All right, the 7 deflections, and that's how the basin will look like. Okay. Now my goal here is I have 7 deflections. Okay, correct? And the instant I hit that load, at that instant, there was only one right value of E1, E2, E3, E4. Everybody agree on that? At that instant when I hit it, there was one E value. I have to be like Sherlock Holmes and try to find what those E values were. You see what I'm saying? Okay. Now, if I must know accurately what these thicknesses are, if I do not, I have a problem. I have 4 unknowns plus another 3 unknowns. I'm in an impossible situation. Does that make sense? Everybody with this problem? Okay. Good. Now, there is a cone of distribution that we discussed several times in the last two days, correct? So when I apply the load, right, the deflection in the center is happening due to all the 4 layers, correct? But right here, it is happening in this particular case due to only E3 and E4. Can everybody understand that why? Because when I hit a load, there is a cone of distribution and the deformation is happening 6 feet apart. Right? 72 inches apart, 5 feet apart. But this deflection, whatever this is happening, is not due to E1, E2, E3, or E1 and E2. Because it is not in the cone of distribution. Can everybody understand this thing? So it is happening between E3 and E4 depending on the thickness. Everybody with me so far. This cone of distribution is also not constant because all the E values are different. But for now, let's assume that they are the same. I don't want to make it busy. Is that okay so far? So, when I do FWD testing, right, my 99%, my goal is to get the property of the top link. That's the one that's failed, right? That's the one I want to replace, all right? Does that make sense? However, unfortunately in FWD, that is the least confidence I have. Because this deflection is happening to all 4 layers. If I don't know confidence of these 4 layers, any of these numbers, my confidence in E1 drops. Can everybody understand that? Okay, let's look at this now. Let's say these 7 happen due to E3 and E4. Correct? So if I am analyzing the data, I have to start from outside, go inside. Right? So what I have to do is, I have to take D7, I'll just call that D7, right? And I have to find the right E3 and E4 that matches my D7. Everybody take me so far. Got it? So what I have to do is, I have to start from outside to inside and keep changing these values till I first match D7. Okay. I want to make a note. There are many softwares out there that will do optimization and curve fitting, and they will try to match even into E4 to D7. How many unknowns? How many points to fit? 7. So there is no unique solution, right? 4 unknowns, 7 points, right? That means you will end up having unrealistic numbers, right? So it will mathematically fit it, but this could give you 1 million, this will give you 2,000, this will give you 5,000, this will give you 6,000, and it will fit perfectly well. Does that really mean this is 1 million? No. Does that make sense? So the mathematical algorithm is not a payments person. Does that make sense to you? It is just doing the curve fitting. Does that make sense? So one way to analyze this is you you are trying to fit all these 7 deflections in such a way. So this is what you see. So you have, these are the measured data, right? And if I hit all the 7 points like that, does not guarantee that I've got the right numbers. Is my point. All right? I have to. So this is how you start. You have to initially start with an initial number of G7. Somewhere you have to start based on experience or whatever it may be. Let's say I start with 500,000, 100,000, 50,000, 20,000. Let's say. It can be from my past experience, whatever it may be. If you see subgrade around 20,000, please put 20,000. Right? If you don't see 20,000, you see 5,000, please put 5,000. Initial number is just the initial number. Everybody will be so far. It takes this, tries to fit them, and it will spit out different numbers. Okay? Very important to note. If I were to take in this location one FWD, 2 FWD, 3 FWD. These are, let's say, 100 feet apart. Okay? This is along the plan view, along the roadway. Question here. If I hit here, right? Barely 300, 400 feet apart, correct? What are my chances my subgrade will change considerably within 400 feet? What is it? It will not change. What is my chances that within 400 feet my subgrade will change? Negligible, right? So you have to run the analysis here, you have to run the analysis here, you have to run the analysis here and here. And let's say you get the bottom number to fit closest to D7 and you get 15,000, 5,000, 3,000, 22,000. This is E4. Unless I have a very definite reason, something went wrong in the water at the subgrade level, these are bogus numbers. Or these are bogus numbers. Can everybody understand what I'm saying? Unless I have a logical reason to believe within 4 points, the numbers drastically change, they should have been very close to each other. Everybody's with me so far. So what I have to do is a couple of things. Average this. Average this. I get an average number and lock it and rerun the thing again. You know what I'm saying? However, you have to make sure that the fit is closed and you end up with a consistent number all through. And not only that, if you know the classification of this subgrade or any historical data of this subgrade which tells you, okay, the range of values are between 10,000 and 25,000, let's say. You need to have an independent check of this 10,000 to 25,000. Okay, I cannot have 5,000 and 3,000. Okay, right? Does that make sense to you? So you start from the outside one, you lock it, you rerun it, and now you have independent confidence. Okay, Now I have nailed my subgrade. Some certainty. Now you move up E3, E2, E1. Same logic there. Pardon?
Assuming the values of modules.
You keep this constant. Once you average this, you lock this number. You have now significant confidence that this number is right. But there's only one right answer electronically, but you don't know what it is. You're just going towards the right answer. Correct? Now you lock this based on what I told you, and now you move up. You do the same logic here. Then you move up. The same logic here. And then you come to E1, which you have the least confidence in, but the most need. And that's how you get E1. That's how you will get your modulus, your composite modulus. Pretty big news so far. Couple of things that will happen, very common. If these thicknesses are very small, one of them are very small, they will tend to swap. I'll explain what this means. That means in one of the sections, mathematically, E3, E2, and E3, one will show 40,000, one will show 5,000. Next section, this will show 6,000, this will show 42,000. So on and so forth. So mathematically, it is not able to lock in, it is just swapping the numbers. Is it really happening? Not possible. Right? You cannot have within 100 feet 40,000 to 6,000, 5,000 to 42,000. But just that this FWD program is not able to nail down that number. What you have to do is, okay, I'm going to combine these two in one. Because my goal is even. Right? So what I will do is I'm going to combine this into a 3-layer system. H1. I'll call this another layer, H2 plus H3, and call this the new E value, and then this number. Got it? And that, you rerun this analysis, and immediately the number will be between the two. And it will be consistent. Now you lock that number, rerun it, and then you get the top. And that's your final answer. So HWD is an art, and many people follow it very blindly using the software, and then they make a mistake. So very, very difficult. I just wanted to digress, but this is a very important topic. Questions for me? Any questions online? All right, let's go through rigid pavement design. Then we'll go to that.